Good afternoon.
Good afternoon, ma'am.
Okay, am I audible?
Yes, ma'am.
Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, then we'll start. So, in the previous class, we see what is functional dependency. So today we'll see some of the things that we can do with functional dependency, uh, and then the things means whatever things we need to know about functional dependency. Okay. So first, this is here you can see in this slide, some inference rules are given. So why this inference rules? So if a functional dependency is given, by using that functional dependency, we can infer other functional dependencies. Okay. So by using this rules, we can means whatever rules that is given here, 8 rules. So for a particular relational model, if a functional dependency is given, then other remaining functional dependency we can determine. Okay, so let us see the inference rules one by one. The first rule is reflexive rule. So this is an obvious functional, I mean, this is an obvious thing. So that is why this is a trivial inference rule. If Y is a subset, uh, if Y is a subset of X, then X can determine Y. So this is a trivial rule. So this is the first rule. Let us see the other remaining rules one by one. The second rule is augmentation rule. If there is a functional dependency, X determine Y. Okay. If there is a functional dependency, X determine Y, then if we add a set of set of attribute Z to X and Y, then this functional dependency also holds. Okay, so that is augmentation rule. And then we have transitive rules. So transitive rules, if X is determined, means X can determine Y, and then Y can determine Z. That means X can determine Z. Okay. So if we have this two functional dependency, then we can add another functional dependency, or you can say we can infer another functional dependency, X determine Z. The fourth rule is decomposition or projection rule. So if we have a functional dependency, X determine Y, Z, then we can decompose into two functional dependencies, that is X determine Y and X determine Z. Okay. The opposite of this decomposition is union or additive rule. So this, if we have two functional dependency like this, which hold for a particular relation, then this functional dependency also holds on that particular functional relation. Okay. Next one is pseudo transitive rule. So if we have a W like this, if we have two functional dependency, X determine Y and WY determine Z, then we can combine W and X and we can determine Z. Okay, because by combining Y and W, we can determine Z. Okay, and this Y can be determined from X. So that means by combining X and W also, we can determine Z. So this is pseudo-transitive rule. Next is composition rule. So composition rule means two functional dependency, we can combine it. Okay, like this. Means the left-hand side and the right-hand side, we combine the set of attributes, and this functional dependency also holds if these two holds. Okay. The last one is general unification. So if we have, you can see here also, if we have two functional dependency like this, then by removing Y from W, okay, if Y is a subset of W, they are all a set of attributes, isn't it? Whether it is X or Y or Z or whatever we are using here, they are all set of attributes. So if Y is a subset of W, then after removing Y from W and performing the union between them, between this X and the Y minus Y, W minus Y, we can determine the combination of this Y and Z. Okay, Y determine Y and Z. So these are some rules by using which we can infer many other functional dependencies. if some set of functional dependency is given. Okay, so the most important rules from these 8 rules are these 3. Yeah, and these 3 rules, 1 to 3 rules, are known as Armstrong inference rules. Okay, Armstrong inference rules, and by using these 3, we can get all this other remaining functional dependence. Sorry, all this other remaining inference rules. Okay, so by using the given functional dependencies in a particular relation, if we use these 3, only by using only these 3, we can determine all the possible functional dependency of the relation. Now, why we are why we have to do this inference? So we are inferring means we are deriving many other remaining functional dependencies from a given set of functional dependencies, so that we can perform many other there are very important tasks we can do by using the concept of inference. Okay, and those things I will just tell you one such example. By using this inference rules, or whether another thing is by using the concept of closure, we can determine candidate keys. Okay, we can determine candidate keys of a relation, and also we can find and cover or equivalence of functional dependencies. So there are some few things that we can do by using these concepts. Okay, so after this another thing that we need to know about functional dependency is closure set. So what is this closure? Closure, this means if a set of functional dependency F is given. Okay, if a set of functional dependency F is given for a relation R, then by using F, if we can infer more functional dependencies, then the union of this F with the inferred functional dependencies, they are known as closure of the F. Okay, so even the definition is given here. F is going to be the given functional dependency, and F plus represent the closure of F. Okay, F plus represents the closure of F. So how we are going to find this closure of F? We can find it by using inference rules. The first one is by using inference rules, we can find closure of a functional dependency set F, which is represented by F plus. Now, what is this F plus? Let me just read it out. Set of functional dependency that can be inferred from F, including F. Okay, so we will be inferring functional dependency from F, including with those inferred functional dependency, and this F, including these two, means combination of these two will be the closure of F. That is F plus. Okay. The set of all functional dependencies that include F, as well as all dependencies that can be inferred from F, is called the closure of F, which is represented by F plus. This is another formal definition of closure. So I told you that by using inference rule, we can determine F plus. Okay, and that is even again here you can see the set of functional dependency F plus can be determined from F by using only inference rules 1 through 3 repeatedly. Why? Because 1 through 3 is the Armstrong inference rule, and I already told you this is only the necessary rules that we.
Excuse me.
Yes.
The screen is not visible anymore.
Yeah, I can't hear you. Louder.
The
Speak
screen is
louder.
not visible, I think.
Okay. Yeah, I think I lost the connection. This connection that we're having in NIT Manipur, I don't know what has happened. I'm losing the connection again and again. Just give me some few minutes. Is it visible?
Yes, ma'am.
Okay, so by using only the Armstrong inference rules, that is rule 1 to 3, we can infer all the possible, means we can infer all the possible functional dependencies of F, and that will be the closure, isn't it? The set of dependencies F plus can be determined from F by using only inference rules 1 through 3 repeatedly. So this is one way of finding closure. So closure is very important. So listen here carefully. So when you are given a set of functional dependency F, and if you are asked to find F plus, that is the closure of F, then you can either use rule 1 to 3 to determine your F plus. Okay. Or in another way, you can use closure of attributes, set of attributes. So we will find closure of set of attributes, and after that we can find F plus. So how we are going to do that? Let us see. So we will be determining it by using an algorithm. Okay. So that algorithm is, you can see here, determining F plus from F. The first step, determine each set of attributes X. So this is the steps. Okay. Determine each set of attributes X that appears as the left-hand side of some functional dependency in F. Okay, so we have to determine all the X's, means that we will be having many functional dependency in this F, isn't it? So for those functional dependency, we have to determine X's. After that, we will find closure of X, that is closure set of attributes. Okay. So the second step is determine the set X plus of attributes that are functionally determined by X based on F. Okay. So we will be getting this X plus based on the given F. Okay. So I'll tell you later on how to find this X plus but for now, the steps for finding F plus from F is, first we have to determine X. After that we will determine X plus. Okay, that is closure of X under F. And at last we will include all additional functional dependency determined from all X plus. So after getting X plus, we will be having something. I will tell you what those things will be. And by using that solution, means the solution of X plus, we will determine the additional functional dependencies. Okay, so those additional functional dependency union F will become your F plus. Okay, now this is the algorithm for finding X plus. Now let us see the algorithm for finding X plus. Okay, closure of X under F. So how will we find it? First, X plus we will initialize it as X. Okay. After that, we will perform a loop, and inside the loop, what will happen is all X plus will be X plus. Okay. And then for each functional dependency Y determine Z in F, do again we will check whether Y is a subset of X plus or not. If Y is a subset of X plus, then X plus is going to be X plus union Z. Okay, that is, if we are going to have this X plus, isn't it? We already initialize it, isn't it? And then what will happen again? We will initialize all X plus as X plus. After that, means again and again the value of X plus is going to be changed. It's going to change in each iteration. It will change. So we need to set the all value of X plus here in all X plus. After that, inside X plus we will include a Z. Okay, we'll include a Z. If there is a functional dependency, Y determine Z, and Y is a subset of X plus. If these two conditions holds, then we will include Z, means we will just include Z in your X plus. And this is going to be the new value of X plus. We have the old value of X plus, and we have the new value of X plus. We will check whether these two remain same, means there is no changes in your X plus. At that point of time, we will means we will end this iteration. Okay, like that we are going to determine your x plus. Any doubt here? This is very important algorithm. You have to remember it. What is this x? Tell me. What is this x?
Closure of X.
No, no. This x. X. X plus is closure of x. Okay, but what about this x? What is this x in F? By using F, what is this x?
Ma'am, attribute.
Set of attributes that is there in the left hand side of a functional dependency in F. Isn't it? F is a set of functional dependency. Given functional means this F is will be given to you. Okay, F will have set of functional dependencies. And in those set of functional dependency, we are going to get the left-hand side, a set of attributes that we have in the left-hand side of the functional dependencies. And those are known as, we will name it as X. Okay, it got disconnected again. Okay, let us see an example. Then you will understand it better. So here, this is an example. A relation is given and a set of functional dependency F is given. Okay, so here we have three functional dependencies. The first one is this one. That is S, and these are all sets, isn't it? That is why we are enclosing them by using the curly braces. So set of here SSN can determine e-name project number. So that means this is the first functional dependency that we have in F. After that, we have another functional dependency. Here, project number determine project name. And then the last functional dependency, we have SSN, combination of SSN and project number can determine hours. Okay. So these are all sets, X and Y's. Okay, X and O, this is X, this is Y, this is X, this is Y. These are X and Y's in the definition of functional dependency that we see in the previous class. So X is also a set, Y is also a set, isn't it? So that is why we are enclosing them in a braces. Okay, so we got three functional dependency in F. We have three functional dependency in F. F is again a set. Okay, F is also a set. This is a set of functional dependency. That is why all the functional dependencies are enclosed by braces and they are separated by commas. You can see. Okay, so remember, means this is F is also a set. Now F plus is also a set. So we are going to find F plus, that is closure of F. How we will find? Before finding the closure of F plus, again it got disconnected. Wi-Fi, yeah, bro. Okay, so we are going to find f plus by using the given f. Okay, so for that we will find x plus, that is the closure of the set of attributes, and those x are going to be the left hand side of each functional dependency that we have in f. So the first x we will take this SSN, the second x we will take this project number, and the last x we will take this set, that is SSN and project number. Okay, so first step we will find here, you can see closure of SSN, that will be represented by SSN plus. Okay, so again it is going to be a set. Okay, set of attributes will be there. So for SSN plus we will be using this algorithm. We are going to use this algorithm. What is that? We have to search for the functional dependency in f one by one, where y is a subset of your x plus. Okay, first it will be initialized as like this. Okay, x plus will be initialized as x. Initially it will have the value of x. Okay, and then we'll check whether there is any functional dependency y determine z where your y is a subset of x plus. If there is such type of functional dependency, then we will include z in our x plus. Okay, so that is how we are going to determine the closure of x. We will repeat it again and again till x plus is your all x plus. Means if it remains unchanged, then we'll stop there. Let us see. So SSN, first it will be initialized and it will contain only SSN, isn't it? It will be initialized to x. So that is why we will have SSN in our x plus. Okay. After that, let me just remove all these things. So initially it will contain only SSN. Okay. After that, we will go for this functional dependencies one by one. And we'll check whether there is any y determined z. Okay. Where y is a subset of x plus. Okay, so this is going to be x plus, isn't it? So let us see the first functional dependency. Here you can see this is y, and this y is a subset of x plus, isn't it? Because we have this SSN here in the set. So what we are going to include here, tell me.
Ename
name.
number.
Ename and
Ename.
project.
Yeah, ename and project number. So we'll include ename and project number. Okay. Now we'll check for the next functional dependency. This is the next functional dependency. Now we can again see that project number is a subset of this, isn't it? So we'll include project name also here in the set. Okay. Next functional dependency, this functional dependency SSN project number is also a subset, isn't it? This is also a subset of x plus. So again, ours will be included. Okay. Now we will check for, means we have to repeat it again and again until until it remain unchanged, isn't it? So we will check for the means again we will repeat the same process from the start, from the very beginning of the functional dependency. So we'll check it again. Already they are included, so it remains unchanged, isn't it? When it remains unchanged, we'll stop there. Okay, and the value of SSN plus is this one. Okay, so this is the resultant closure of SSN. Same thing for project number also. At first it will contain only project number. We'll check the first functional dependency. This is not a subset. We will check the second functional dependency. This is a subset. Okay, so if this is a subset, then we will include project name here. Okay, and then again the third one, this is not a subset, so it will be, means we are not going to include ours. We'll come back again and we'll check it again, and at some point of time it will remain unchanged. So your project number plus is going to be project number and project name. Let us do the last one. So initially it will have only SSN and project number because of the initialization that we have. So after that, what we are going to include, SSN is a subset, so we will include ename, and project number is there, already there. So as it is a union, so we do not need to put another project number because union will eliminate the redundant attributes, isn't it? So it will be eliminated. Now the next functional dependencies here, Y is project number and project number is there in the set. So it is a subset. Now we will include project name because of that. After that, SSN and project number is there. So ours, we will include ours also. Okay. Now we'll repeat it again. SSN is a subset. So we'll include project number and ename. And then we'll repeat again. Then at some point of time, it will remain unchanged. So at that point of time, we'll stop. Okay. So like this, we'll be finding the closure of a set of attributes. So we know how to find the closure of a set of attributes. Now, after getting all this, we can say that your F plus, we will have this 3 functional dependency. Along with that, we will include the other remaining functional dependencies. So instead of including all of them, I will just put the remaining attributes there in this functional dependency. So SSN can be able to determine SSN, means it will be able to determine ename, project number, project name, and hours. All this 4 attributes it will be able to determine. So I've included all of them here, you can see. Okay. Initially, it was only able to determine ename and project number, isn't it? But I have included because after finding the X plus, we know that it should also be able to determine project name and hours. So we will include this also. Okay. And from the second thing, it will be able to determine only project name. So nothing is included. It means the same dependency we have here. The last one, SSN project number can determine ename, project name, and hours. So we have included some few functional dependency here in F plus. Okay. So like this, we can invert by using F, we can invert F plus. Any doubt? Closure of a set of attributes also tell us that we find a closure of a set of attributes like this. Also tell us that whatever we got here will be able to determine from this X or this SSN. Okay, same thing again. Whatever we got here in the X plus will be able to determine from your X. Okay, so that is another way of representing your closure. Now let us see some few more examples. Here you can see given relational schema are some relational schema is given. So R is the name of the relation and P, Q, R, S, T, U, V, they are the name of the attributes. Okay. Having following attributes, this one. Also, there is a set of functional dependency denoted by FD, and the set of functional dependencies are this. Okay, so we have 3 functional dependencies in FD. P determine Q, QR determine ST, PTV, combination of PTV determine V. So you can write the functional dependency like this also without enclosing them in the this one in the curly braces. You can write like this also. Okay, so they are same. You have many ways of representing the functional dependencies. You can enclose it inside the curly braces. That is also correct. You can write like without the curly braces also. That it is also correct. Okay. So for this relational schema, the given relational schema, a set of functional dependencies is also given. So what we are going to do now, determine QR plus and PR plus. that is closure of QR and closure of PR. Now tell me, what are the attributes we are going to get here? Means that without curly braces, the sets are given, is it? So we will not use curly braces. Tell me, what are the attributes that we will have in QR plus? Initially, it will be
QR.
Yeah, it will have QR. After that, what will happen? We'll check this one. P is not a subset of QR plus, so we are not going to include Q here. Now QR is a subset of QR, isn't it? Now what we are going to include? ST, isn't it? PTB is not a subset of this QR plus, so we can't include this. B will again come back here. P is not a subset. QR is a subset. So we do not need to include it again because they are already included. A is equal to B. So when we repeat here again, it remains unchanged. Okay. That means QR will be QRST. Now what do you get for this? Tell me. Try this. PR Q PR QST V. How will you get? Okay. Let me see. Will it have B too here? Yeah, ST. P is there, T is there, B. B is not there.
Yeah, ma'am, we will not.
B will not be there.
Yes, ma'am.
Yeah. So PR plus closure of PR is PRQST. Okay. Any confusion? Any doubt? You have to master in finding the closure of set of attributes. So if you have any doubt finding the closure of set of attributes, then you can tell me. This is a very important topic. Okay. Now let us see another example. Let R be a relation with having attributes A, B, C, D, E, F, functional dependency F, and a set of functional dependency F. Which of the following is a key or candidate key? Okay, now by using functional dependency, we can find out candidate keys. Okay, so already some attribute sets are given. So from here, we are going to check which is a candidate key for the given relation R. Already answers are given, means some possible answers are given. What will happen is, I already told you that closure means closure of a set of attributes means inside the closure, whatever attributes we got are going to be able to determine from the given set of attributes. Okay. Okay, that means when we have a closure, when we have a X like this, CD, X equal to CD, this is going to be your set of attributes, given set of attributes, isn't it? CD, whatever we got in CD plus is going to be the attribute set of attributes which can be determined from CD. Okay. Here you can see QR, from QR, whatever we have here will be able to determine. That means from here we can conclude that many functional dependency, we can conclude many functional dependency from here. So I'll just use this in order to represent arrow. Q will be able to determine, QR will be able to determine Q, QR will be able to determine R, QR will be able to determine S, QR will be able to determine T. So these are the functional dependencies that we can conclude from this closure. Okay, when we have a closure, then these are we can conclude this. That means Q can be determined from QR. R can also be determined from QR. S can also be determined from QR. T can also be determined from QR. That means by using some inference rules, means we can combine it, and instead of writing four functional dependency, we can just write QRST. Okay, QRST can be determined from QR. Means if the value of QR is given, you can determine the value of Q, you can determine the value of R, you can determine the value of S, and then you can determine the value of T. Okay, so this is the definition of your closure. Now, which of the following is a key or candidate key? So what is the definition of a candidate key? Tell me. What is the definition of candidate key?
Ma'am, key is determine all its attribute.
Key should be a set of attributes which can be able to determine all the other remaining attributes, isn't it? Means it can uniquely identify the values of the other remaining attributes. So same thing. Now what you can, from those two concepts, what you can get it is, if the closure of CD contains all the attributes, then CD is the candidate key. Okay, from those two concepts, what you can conclude is, if closure of CD contains all the attributes, then it means CD is a candidate key. Okay, same thing, if CE, closure of CE contains all the attributes, then CE is a candidate key. Closure of AE contains all of them, then AE is a candidate key. Like that, those two things, by using the definition of closure and by using the definition of candidate key, you can conclude this thing. Okay, now let us find the closure of CD. Closure of CD will contain CD, and then it will have F. Yeah, and then
Just that much.
that's it, is it? Okay, now what about closure of CE?
CE.
This will be candidate key.
CE, and then it will have A, and then F, and then other
D,
and
then AB.
D will be there, and then B will also be there.
Yes.
Okay, that means I will, instead of writing like this, let me write A, B, C, D, E, and then F. Means CE can determine all the attributes. Is it? What about AE plus? No. If we got the answer, then we do not need to check for the other two remaining, but still let us find it out. AE plus will be A, E,
And B.
B. Okay. What about AC? AC plus, closure of AC? A, C, F, ACF, B. Okay. Now, which one is going to be the closure? The correct answer is this, isn't it? B. Which of the following is a key or candidate key? The answer is going to be B. Okay. So like this, you can find out candidate keys by using functional dependencies, set of functional dependency over relation. Now let us see another example. Let R be a relation this, having the functional dependency this. Find candidate keys. Now here what is happening is, here what in the previous example, some options were given. That is why by just determining the closure of these options, we got the candidate key. But if there is no such thing is given, no such options are given, then what will happen? By using the functional dependency, you are going to determine the candidate key. Okay, means we have to determine it from the functional dependencies. So for that, the first thing you need to get is the essential attribute. So what is this essential attribute? I'll tell you. The functional dependencies that we have. The first, the attributes are A, B, C, D, E, F, G, H. We have A, B, C, D, E, and then F. Is it A, B, C, D, E, F, G, H? G, H. So we have these attributes. Okay. These are the attributes that we have here. Now about the functional dependence. Now the functional dependencies that we have here in the given example is AB can determine C. AB, by using AB, the set of attributes AB can determine C. Okay, and A can determine B. So functional dependencies can also be represented like this. Okay, so A can determine DE. A can determine D. By using this arrowheads, you can represent the functional dependencies like this. So there is an arrow from AB to C, isn't it? Same thing here. From AB to C, there is an arrow. From A to DE, there is an arrowhead. So you can represent it like this also. So there is the third functional dependency is B to F. B to F. I should have some more gaps here. Okay, now B to F and then F to GH. GH. So these are the set of functional dependency that is given. Now, what is going to be the essential attributes? So essential attribute for a candidate key is to be the attributes which cannot be determined from any of the attributes. Okay, which cannot be determined from any of the attributes. That means which does not pointed by the arrows, which is not pointed, which is means there is no incoming edge of this particular dependencies. And which is going to be the essential attribute in here, which is going to be the essential attribute in the given relation?
AB.
AB, yeah, AB. AB is going to be the essential attribute. What does it means? Means AB cannot determine from any of the attributes. AB, by using AB, you can determine many other attributes, but you can't determine the value of AB from any of the given attributes, because there is no such functional dependency where you can be determining AB from any of the other remaining attributes. Okay, so AB is the essential attribute. So why I'm drawing like this? Because the attributes which does not have any incoming edge is going to be the essential attribute. Here we have A and B. Here A, B doesn't have any incoming attribute, isn't it? They are all outgoing. Okay, there is no incoming edge from A, incoming edge to AB. Okay, so that is why AB is the essential attribute. Now, after getting the essential attribute, what we are going to do? Either essential attribute is a key, okay, or essential attributes are part of key. Why? Because if AB cannot be determined from any of the remaining attributes, then AB should be there in the candidate key. Okay, because AB can determine AB itself, isn't it? A can determine A itself, B can determine B itself. Okay, other remaining attributes cannot determine AB, so they should be there in the candidate key. Okay, both A and B should be there in the candidate key. So either the essential attribute is the key or essential attributes are part of key. Okay, so what we are going to do is we'll check whether this is true, whether the essential attribute is a key. For that, what you need to do, you need to find A, B plus. I will write like this. it should be subscript here, okay, but means superscript here, but I will write it like this. We have to find AB plus in order to check whether AB will be able to determine all the other remaining attributes or not. Okay, let us see. AB will contain AB initially. After that, let us see the functional dependency. AB will also have C, and then it will also have DE, and then it will also have F. If it has F, then it will also have GH. Okay, that means AB can determine all the attributes that we have in R. So we can now conclude that, here I'll write the answer. Candidate E is your AP. Okay. There is going to be a single candidate key here. You can have many candidate key in a relation, isn't it? So for this example, there is going to be a single candidate key, and that is AB. Okay, any doubt? We'll see some few more examples in the next class. So this is one such example which has only a single candidate key, and here the essential attribute itself is the candidate key. We'll see some more examples where this is not going to be the case. Candidate key means the essential attributes is not going to be the candidate key, and there's going to be many candidate keys. So we'll see those examples in the next class. Okay, now let me take the attendance. Abhijit,
Present, ma'am.
enrollment number 1, present.
Present.
2,